So, in my opinion, I think it's okay that there are different definitions of biomimicry. We're pretty used to this in biology, where it's hard to even define what life is or what a species is. I take a pretty broad and holistic approach to biomimicry and think of it as drawing inspiration from any kind of discovery about the natural world, about how it works and the processes involved in the natural world, and applying them to some problem in human society. So classically, spider silk has been one of the, I can't think of the word, poster childs for biomimicry, so to speak, because of its incredible properties, and the idea is to mimic those properties in some sort of synthetic fiber, the strength and the high toughness of the silk. But a lot of our research shows that there are many other interesting aspects to spider silk and webs that could potentially be applied to really unique, novel types of problems. So right now we're really interested in the way spider glues function and how we can take some of the principles that are involved in making a spider web sticky and transferring those to new types of adhesives that could be used in novel applications. So do you start with a human-centered problem or start with the discovery in the natural world? That's a great question, and I don't think there's a single approach. In my instance, my research is really driven by an intrinsic curiosity about the way nature works. So I'm very much a bottom-up kind of researcher, and so I go out and investigate how spiders work, how they fit into the natural world, how they evolve, try to understand silk, and then layer on top of that, thinking about, well, what can this knowledge do for society? So what would you do with some sort of synthetic spider glue, in other words? Yeah, there's a real need for new types of adhesives for a variety of different situations. A lot of these are going to potentially see use in medicine, but also there's more and more interest in how do we develop adhesives that can be basically smart materials and respond to changes in the environment. And that's really what we're interested in with these spider silks. A lot of what determines just how sticky a particular piece of silk is comes from the environment, how humid it is, how hot or cold it is. And it turns out that the chemistry of the compounds in that glue droplet affect how it responds to the environment. So by understanding what makes a particular spider silk become stickier as the day gets more humid, while another species silk becomes stickier as the day dries out, we can actually design adhesives that will work optimally under very precise conditions. I work a lot with colleagues in polymer science and in engineering. These are natural relationships because silks are polymers as proteins, and to understand anything about how a web works, you have to think about its design from kind of an engineering or physics principle. So one of the real challenges for biomimicry is learning to communicate across disciplines. And my most positive experiences have come from working with people who maybe you have to learn their language, but who are really interested in your perspective about the situation. So I think both the biologist and the engineer, the lawyer, whoever's on the other side of the spectrum, they have to not just want to solve their own problem, but learn about that problem from the other person's perspective. Well, part of the answer to that question is we have achieved better adhesives. We have achieved better fibers. They might not quite match what's happening in nature, but these are very, very complicated processes, and sometimes it takes years of investigation to discover what the complexity is, let alone to then understand that complexity. And that's definitely true in the case of spider silks, where initially the interest was in, let's look at the molecular structure of the silk. And researchers discovered that it has this nanocomposite structure, little tiny crystals embedded in kind of a fluid matrix of proteins, and this made it such a super tough material. And all we have to do is put that into some synthetic fiber. But in the case of spider silk, there's a lot of extra complexity, a lot of tricks, so to speak, that are involved in how can you first produce these molecules, store them in a liquid state, and then spin them into a solid fiber. And all of those tricks and processes have to be understood to be able to move that to some industrial scale operation. Right. So incorporating a strong evolutionary perspective is one of the really unique features of my research group that distinguishes us from lots of other labs working on silk. So I'd say some of the advantages of taking this kind of approach would be that we can change what you're really trying to model. Most people work on a single species of orb-weaving spider, basically the white lab rat of the spider world, if you will. And so they understand the properties of that spider's silk, the molecular structure of that spider's silk, and the morphology, the shape of the spinning gland of that spider. But let's say you don't need to exactly copy that. You want silk that maybe needs to be strong, but not necessarily as tough as that spider silk. Well, I can show you where in the evolutionary tree those species exist, and I can show you that. In fact, their proteins are pretty different looking. The complexity of their spinning glands isn't the same as in that orb weaver, and it might actually be an easier model to go and mimic in an industrial setting. This is a really interesting question because there needs to be some feedback from the technology and to the basic researchers. And this has definitely been important for silk research. So technology's played a role in basically two big fields. One would be the increase in our ability to look at the genetic sequences of the proteins that compose cells. There's been an exponential increase in our knowledge of the protein composition of cells. And the other one is actually my specialty, which is our ability to look at the actual mechanical performance of silks. 10 to 15 years ago, we were limited to investigating properties of only the biggest species of spiders, silks, and working with bundles of many, many fibers. Now, with modern mechanical testers, we can look at individual fibers spun by very small species of spiders. So this greatly enlarges the amount of the evolutionary tree of spiders that we can actually investigate and learn from. So I think there's two ways to answer why the Great Lakes region is becoming a biomimicry hotspot. One would be this kind of combination of, we do have a latent industrial capacity from our manufacturing past that's sitting around kind of unused, looking for something to do, so to speak. And we do have a great system of very good universities that are generating a lot of the basic knowledge as well. And then in between them, we have this amazing network of small companies, startups, focusing on mostly materials, polymers, and biomedicine in the region. So we kind of have the complete continuum from investigating the natural world to developing and ultimately building products, bringing them to market, all waiting to work together in the region. And then secondarily, I say we've been very fortunate in just attracting a few different people who are really energized by this idea of biomimicry and are working together very synergistically to make it happen.